All right, good evening and welcome to lecture number 8 for MT225. Let's see here. Tonight, we're going to be extending some of the ideas that we worked on last week. Last week, we worked on equilibrium of concurrent coplanar force systems, and we'll review that just a little bit. Um, and then we'll extend things a little bit. We'll see a situation where just having the sum of forces going to zero doesn't necessarily guarantee we're in equilibrium. And so we're going to have to look at those situations a little more carefully. That's what we call what happens in a non-concurrent force system. So we'll see how the non-concurrent system works, and we'll work with that this week. Uh, Early warning on it, I suppose, is we're probably looking for our first exam coming up a couple weeks from Wednesday. This week we're going to be finishing non-concurrent force systems. Next week we'll add a little bit more into it on Monday night. I will assign a homework assignment next Wednesday, but since that would be due on the same night we'd have the exam, which would be March 17th, if all of the schedule works out. It'll be March 17th. The I don't like having a homework assignment and an exam due on the same night. So the homework assignment is going to be a bonus assignment. That is, you can do that assignment, turn it in, and it will count for, it'll replace your lowest homework grade, either up to this point or at any point in the future. So you could think of it as a way to buy yourself out of having to do a future homework assignment or replace one of your previous ones that didn't go so well. So you don't have to do it. Doing it won't hurt, not doing it won't hurt you, but it should be practice for the exam because the content that is on that homework assignment, which would be, I think, homework number 5, that will be game for the exam. So we're looking at 2 weeks, and no matter what we do with respect to a classroom, Wednesday night, 2 weeks from now, if that's our scheduled exam date, if we everything goes according to plan, that will be in a classroom. So make sure you're ready for that. All right, so let's proceed here. Homework 2 I sent back over the weekend, and for the most part, not really any major difficulties. A couple people got tripped up in signs on the directions when they were adding together their vectors. So you got to be careful of that. You got to look at that, look at the directions your vectors are in. If they're to the right or up, they go into the sum positive. If they're down or to the left, they go into their sums negative. So don't get lost in those minus signs. And the solutions for that have been posted. Also, homework 3 has been posted. Homework 3 is due on Wednesday, and I'll open up the floor for questions on that in a moment. Quiz 2 is also up. I've gotten a couple submissions on it so far, but there's still plenty to come in. So that's on the website, and the website should be back up now. We had a little bit of a power failure earlier today that took us down for about an hour or so, but we're all back up online now, so you should be able to get a hold of the quiz. If for some reason power goes back down because it is a little bit windy out there, I will use another vector to get you the quiz. I'll email it out to everyone, regardless of whether you've submitted it or not. So as long as you can receive email through your selected source, you should be able to get access to the quiz. The quiz is on the homework 2 content, and the solutions are up there. So if you had some problems on homework 2, might not be a bad idea to take a look at those solutions before you tackle the quiz. All right, so speaking of homework, on homework 3, so concurrent force systems. Anyone have any questions on that so far?
Would we be able to go over one of the problems?
Well, on Monday nights, typically what I'll do is I'll give you a little bit of guidance on setting things up, but I won't actually work the whole problem out. If it's still an issue on Wednesday night with that same problem or with even a different problem, that's when I'll work it out in its entirety. Is there a particular problem you have in mind?
Number 4.
Number four, is that the box on the slant
Mm,
on the ramp?
Yeah,
Yep.
yeah.
Yeah, that's a pretty common one, and it's don't worry about having experiencing potentially some challenges with that one because some of the problems I put on the homework assignment, I intend those to be ones we end up going over in class. So it's a good problem to take a look at. So let's get the setup going here, and let me go over to the display. So let's see. Let me pull it up here first. So there's homework number 3, and there's the problem there. So we've got this 20-pound box hanging from a wire, and it's on this 30-degree incline. And we want to find out what the tension is in the wire. So that's 20-pound box held up by a wire. All right, so it looks something like that. So there's our 20-pound box on the wire. There we go. So the first thing we have to ask ourselves is, do we believe this is in equilibrium? Does this look like it could be a static situation? And I would hope that your instincts would say that it should be. You could certainly imagine setting this up, tying it up to something, tying a rope up to something on an incline and having it stick there. So as long as the tension can be handled by the rope, then it should stay stationary. If that rope were to break, well, then we'd have a dynamic situation. So the part of dealing with this problem is dealing with the fact that we've got this incline, and let's go ahead and run our regular setup on this, going through the setup for a concurrent force system. For a concurrent force system, the first thing we have to do is draw a free body diagram. So we have to first figure out what our body is. And in this case, our body is going to be the box. And last week when we talked about free body diagrams, one of the kind of hints I gave you here, or I suppose tools I gave you here, is to think of this system boundary, this bubble that you can shrink down to the object that you're interested in, dividing it between itself and everything else, the universe inside and outside. Um, Anything that touches or crosses that bubble has to be represented in the free body diagram. The only thing that isn't crossing or touching that we can see physically would be gravity. Gravity would be the only force we deal with here that would not be readily visible. So let's go over to the right side here and we'll draw our free body diagram. So the free body diagram is going to start with the body, and I'm going to draw it in basically the same kind of orientation. But remember that the point of the free body diagram is to eliminate all those things that are supporting the object. And anytime something touches or crosses that system boundary, there must be a force there. So I think everyone could agree here there must be a force on the box due to the tension in the wire. The wire or the rope crosses the boundary pretty clearly there. And then we also have weight pulling down. We have this 20-pound force pulling down. But there's another force here because just these two forces, if you think about these two, those two can't be in equilibrium. Because if you had something pulling down at the same time as something pulls up and to the left, this thing would move. This isn't a tug of war, no one's winning. These two forces are helping each other and they're kind of pulling off in this direction, off to the lower left. If you added up those two vectors, you'd get something off to the lower left. There must be another force in the system, and there is. There's this force of contact between the surface of the ramp and the box. The surface of the ramp exerts a force on the box, just as if you were standing on a floor somewhere. If you stand up wherever you happen to be, your feet are going to be planted on the floor. The floor is pushing up on you to cancel out your weight. You are in equilibrium because gravity's force is canceled out by this force exerted by the floor. Now, surfaces like floors and such generally exert forces perpendicular to their surface. So if you're standing on a floor, you're pushing down due to your weight, the floor is pushing you up to cancel that out, perpendicular to the floor. Well, there is a perpendicular force here also, but because of the angle, this 30-degree angle, that force is up and to the right by an angle of 30 degrees. So if we put some angles in here, that's 30 degrees because the tension is parallel to the ramp. This one's 30 degrees because this force, what we call the normal force, so N stands for normal, and normal is just a mathy way of saying perpendicular. Normal has fewer syllables than perpendicular, so it's easier to say. So the normal force is perpendicular to the surface. When things are normal in math and vectors and such, they're perpendicular. Now that has a chance. This free body diagram has a chance of being in equilibrium. You could buy that these three arrows pulling in the way they're doing should cancel out, or at least have a chance of canceling out. There doesn't necessarily look like there's going to be a clear winner here. So that's what the free body diagram looks like. Now, in order to do any math with the vectors that we've got here, we've got to define a coordinate system. And if we go and use our traditional coordinate system, where horizontal is x and vertical is y, we can break up those forces into components. You can figure out how much of this normal force is in the y direction and how much is in the x direction. How much of the tension is in the x direction and the y direction. How much of the all of gravity here being in the y direction. And then you've got your equations of equilibrium. You take your sum of forces, set them equal to 0. With this setup, you will end up with a set of simultaneous equations. But we did a problem similar to that last week. So if you are not feeling too clear and comfortable on solving realistic problems with simultaneous equations, go back and look at the videos on that. I think that was probably last Wednesday, Wednesday's class. So you can go back and look at that and kind of follow the procedure there, and you'll be able to figure out values for t and for n. Does that help a little bit with the setup?
Yeah.
Any questions there?
I think no. I think I have a better shot at getting it now.
And like I said, we'll probably have people with questions on Wednesday night. Not everyone's necessarily gotten a chance to look at it yet, but we'll likely have questions on this one Wednesday night. So I'd probably end up working it out. And I'll also show you another way to approach this problem that can make the math a little bit easier. But you certainly have the tools at this point to be able to handle this problem. And we've done an example somewhat similar that involves similar math anyway to be able to solve that. Any other questions on the homework? All right then. Well, let's go back to the notes. So today, our objective is to take a look at equilibrium, but in a non-concurrent force system. So the first thing I'm going to have to do is define for you what a non-concurrent force system is, and then we'll see why in a non-concurrent force system we have some issues trying to figure out if something's in equilibrium. and we'll figure out how we can fix those problems and solve some new arrangements of forces. So let's review what we did last week, essentially, just what we set up in the homework problem. In a concurrent force system, it was enough that we have all of the forces add up to zero. That guaranteed equilibrium for us. In a concurrent force system, the lines of action of all the forces intersected at a single point. So if we go back to our setup here from the homework assignment, you can see the fact that this is a concurrent force system because all three lines of action intersect at one point. That's a concurrent force system. And solving the concurrent force system is just about finding the sum of forces, setting them equal to zero, and solving for your unknowns. In a concurrent force system, life is kind of simple. Now, this is a little bit of mathematical overhead or and such, but it's worth taking a look at because it does come up in a lot of different areas. You hear these two terms come up quite a bit in a lot of mathematical contexts. We call them necessary and sufficient. Necessary and sufficient are conditions. They're describing conditions on something. And if a condition is necessary, it means it needs to be there. So, for example, for something to be in equilibrium, it is necessary that the sum of forces add up to zero. We can't have equilibrium if that's not the case. If the sum of forces add up to something other than zero, we're going to have acceleration. We're going to have motion. That's not static. That's not equilibrium. So it's necessary to be in equilibrium. You must have that the sum of forces equals zero. Sufficient says something a little bit different. Sufficient says it's enough. This condition is enough to guarantee this situation. In a concurrent force system, it is sufficient that the sum of forces equals zero. It's enough that the sum of forces equals zero to guarantee that we're in equilibrium. So necessary and sufficient kind of go both ways. It necessary takes you one direction. It says if you're in equilibrium, you need to have the sum of forces equal to zero. Sufficient goes the other direction and says if you have the sum of forces equal to zero, then you're in equilibrium. And that's described here. It's the idea of necessary is that if we're in equilibrium, the sum of forces is zero. Sufficient means that if the sum of forces are zero, we're in equilibrium. And that is true for concurrent force systems. We're going to see in a second here, though, it's not true for non-concurrent force systems. In non-concurrent force systems, we can have the sum of forces equal to zero, but not be in equilibrium. And you might wonder, well, how can that be? How can we possibly have the sum of forces equal to zero, but not be in equilibrium? Well, let's try it out with an example. Let's take, for example, two equal but opposite forces on a box. So this is a top view of a box sitting on a table somewhere. We have one force pulling on one corner. Let's say it's 20 pounds. So 20 pounds of force pulling on that box to the left. We could have another force with 20 pounds pulling to the right. Now, if we did the vector sum here, we've got two vectors. They're both horizontal, so they're both all x component. We've got a negative 20 here and a positive 20 over here. Well, that's zero. Sum of forces is zero. But I would hope all of you would look at that and rely on some of that physical intuition of yours and say, well, that's going to move. As soon as these forces start pulling, this thing's going to move. In fact, it's going to undergo a special type of motion that we call rotation. So this is going to rotate. Rotation is motion, and motion means we don't have equilibrium, at least not in the case that we're looking for. We're not looking at constant motion. This is going to accelerate. It's going to angularly accelerate. It's going to spin up, or at least it's going to go from where it is to some new position. So even though the sum of forces equaled 0, we still had something that's not in equilibrium. But notice where the lines of action of these forces are. The lines of action of these forces are horizontal. They don't intersect. That's very different than our concurrent force system, where all the lines of action intersected at a single point. When we have non-intersecting lines of action, or when we have multiple lines of action that don't intersect, that all intersect at different points, we have the possibility for rotation. And all of you have been through the AMP program, and you know what causes rotation at this point. You know about moments. Moments, otherwise known as torque, are turning forces, forces that get rotation to happen, or potentially stop rotation. Think about what you did in fluid lines and fittings. Whenever you torqued a fitting, you had another wrench on there providing backup torque, providing counter torque, so that you didn't damage the fitting or twist the line or anything like that. Two torques opposing each other. That's what we'd have to do to stabilize this box. If you think about how you would prevent this thing from rotating, hopefully your instinct says, well, I just reach in there and I'd grab onto it and try to twist in the opposite direction. That would counteract the moment caused by these two forces. So moments work their way in when we have a non-concurrent force system. We don't have moments in a concurrent force system, because in order to have moments, as all of you know already, but we'll review momentarily, in order to have a moment, you've got to have an arm. You've got to have some distance from a pivot point or a reference point. If all the lines of action intersect at one point, there's no arm. Everything's pushing or pulling on the datum. So there's no moment. But when the lines of action do not intersect, or intersect at multiple points, now we have arms. And arms create moment. Arms and force together create moment. So if we have non-concurrent forces, we may have a system that's not in equilibrium, even if the sum of forces is 0. So it's still required, if we are in equilibrium, to have the sum of forces equal 0, but it's not enough anymore. It's not sufficient anymore. The sum of forces equals 0 does not guarantee equilibrium when the lines of action do not all intersect at one point. So we need another condition. We need something else we can put along with that and say, well, if the sum of forces are 0 and this other condition is true, then we're guaranteed equilibrium. And that's where that condition that we have to add in is a condition on moments, is on the moments in the system. So let's review moments a little bit. So moments, for the most part, you're all familiar with. We are going to extend things a little bit. We're going to go beyond where you went in the AMP program, because we did some special things in the AMP program to keep the math easy. But in reality, we can't always guarantee the situation we have in doing weight and balance on an airplane. So we have to be able to handle other situations, and we'll see what those are here. Fortunately, it's not difficult, and you've already got the tools for it. So whenever we have a force applied some distance away from a pivot point, we have a moment or a torque. We say that a force generates a moment. Force with distance, or force along with the distance from the pivot point. That's what generates or creates a moment. So if we go over to the display here, if I have some object, some potato, and I've got a pivot point right here, I've got some place where it's nailed to the wall, but I exert a force over here, that force is applied some distance away from the pivot point. There is a distance in between the pivot point and my force. That distance is what we have come to know as an arm in weight and balance. Distance, arm means the same thing. It's just the distance between the pivot point and the point of application of the force, where the force is applied to the object. Now that will create a moment. That's going to get this thing rotating. And it's hopefully you can look at that. You should be able to look at that at this point and predict that if just this force were acting, you'd expect to see this thing rotate counterclockwise. Now, since everything we're going to be doing is in a flat plane, we only have two options for moments, just like we did with weight and balance. We either have counterclockwise moments or we have clockwise moments. So we only have two options for those. So get used to and think about, as we're working on different problems, the directions that moments are in, whether they're going to be clockwise or counterclockwise. And you can always figure that out, even if multiple forces are acting, by just ignoring every other force and just focusing in on the one that you're interested in, imagining all the other forces go away and just looking at how this thing would move if only that one force were acting. So you can use a little bit of imagination to try to figure out whether you're going to have clockwise or counterclockwise moments. But direction is going to be very important. So moments are twisting or turning forces. We have to have a pivot point and we have to have a point of application. Moments cause rotation or counteract rotation. And we generate moments by letting those forces act some distance away from a pivot point. Now, how much moment we get depends on three factors. Now, you might be saying, hey, wait a minute, we learned to weight and balance, there were only two factors. Well, here there's a third. The distance from the pivot point to the point of application, that's the arm, or sometimes called the moment arm, lever arm, sometimes labeled R or D for the distance from the pivot point to the point of application. You need to have a distance. The bigger that arm is, the more moment you've got for the same amount of force. Smaller that arm is, the smaller the moment is. How much force you've got. So that definitely matters. If you push harder, you should get more moment. Then here's the factor that we didn't have to deal with in the A&P program. We have an angle involved. There is an angle between the line from the pivot point to the point of application and the line of action of the force. That angle matters. How big that angle is or how small that angle is will affect how much moment we have. Now, we ignored the angle in the A&P program. We said it was always going to be 90 degrees. And we do some fairly extreme things in the A&P program to make sure that's true. Think back to what you did in weight and balance last semester or in a previous semester. Before you could do your weighing of the aircraft to figure out the center of gravity, which was basically just figuring out moments due to the weight at different locations, what did you have to do to the airplane? Anyone remember? So what did we have to do before we rolled the airplane up onto the scales or as we were lifting it on the jacks? I know it was a while ago.
Make sure everything was in the located at in the right location.
There's that. You had to make sure it was equipped properly and all that. But there was something a little more fundamental, something you had to go to the TCDS maybe to figure out, or something you had to measure as it was being lifted or as it was being rolled up.
The empty weight.
Well, that's eventually what you were leveling or you were measuring. What I'm thinking of is leveling. You have to level the airplane. The whole purpose of leveling the airplane is to make sure that the angle between the arms that we're using and the weight, the force is pulling down, we want to make sure that angle is perpendicular, that angle is 90 degrees. Because when that angle is 90 degrees, all we have to do to get the moment is multiply the force and the distance. If we could handle a little bit of trig, we wouldn't have to level the airplane. We could just weigh it as it sits. If we could measure the angle of the longitudinal axis to horizontal, and I've done this several times when it's been impractical to level an airplane. For example, if you're doing weight and balance on a tail dragger or something like that, you don't really have the right structure to level it. It's just as accurate to break out the prop protractor and get a really good measurement of the angle of the longitudinal axis, and then take a couple signs to figure out how much moment you've got. They don't document that in the weight and balance handbook and things like that, but mathematically and physically it works out to exactly the same answer. So let's see how that works here. So some terminology with moments. Most of these we're pretty familiar with from our previous experience with them, but the pivot point. The pivot point is the point we get to choose in most cases about which we're measuring the moment. So moment needs a pivot point. We measure the arms from the pivot point. So when we pick the pivot point, that's when we're deciding where we're going to measure everything from. So this is really important. You've got to make sure that when you pick a pivot point, that you stick with that pivot point. Essentially, it's like picking a datum or using the datum that's specified. Once you pick that datum, everything is measured from it. In aircraft that don't have a datum, you get to pick whatever convenient point you want, maybe the nose gear or the main gear, but you get to pick that point. In the end, the math works out the same, but as long as you are consistent in all of your measurements, you make all of your measurements from the same point. So the pivot point does not actually have to be a physical point. And you know this from weight and balance. The datum doesn't actually have to be some physical location on the aircraft. In many aircraft, it's out in front of the nose by sometimes tens of feet on large aircraft. So it's not necessarily a physical point. It's certainly not something the whole airplane would tend to rotate about. So it's just a reference. It's just a place where we reference our moments to. So the pivot point does not have to be a physical point. It's something that any point can work. And if we're careful in picking the right pivot point in a problem, we can make things a lot simpler for ourselves in doing our calculations. We'll see an example of that this evening. Then there's the arm. The arm is the distance between the pivot point and the point of application of the force generating the moment. So if we go back to our drawing here, we've got our pivot point. That's right there. This would be our arm. And right there is our point of application. That's where the force is applied. Now, if we look at the line of action and the direction of the line from the pivot point to the point of application, we get an angle. That's our angle there. Now, the closer that angle is to zero, the less moment we're going to have. Because if the force is pulling right along the the arm, it's not causing rotation. On the other hand, if it gets closer to about 90 degrees, then we're getting maximum moment or maximum torque. So the amount of moment we get depends on what this angle is. The closer that angle is to 90, that is, the closer the force is to being perpendicular to the arm, the more the moment is. The closer the force is to being parallel to the arm, the less the force is. And we'll come back to that in a second. So some important points with respect to moments. Most of these we know from A and P, but this is to summarize that, to review that. When we've got angles involved, only the perpendicular piece of that force, the part that is perpendicular to the arm, contributes to the moment. So that's an important idea, and I'm going to illustrate that for you in a second. Forces that push or pull directly on the pivot point, that is, their line of action shoots right through the pivot point, have zero moment. Think about those times when you had weights at the datum. When you had a weight at the datum, it didn't contribute to the moment. You had a zero arm. No arm, no moment. Any force that's parallel to the arm effectively has a line of action that goes through the pivot point. Whenever lines of action go through the pivot point, that force has zero moment. So think back to what we've worked on with respect to vectors. This force is a vector, and vectors can be broken up into components. Well, there's nothing saying we can't make this force into two components, one that is parallel to the line of action, we could call it F parallel, and one that is perpendicular. We have a perpendicular component. Any force can be broken up into components. If we picked our coordinate system so that our coordinates our axes are along the arm and perpendicular to the arm, we could figure out how much of the force is perpendicular and how much is parallel. The parallel part doesn't contribute to the moment because its line of action goes right through the pivot point. So the moment due to the parallel part is zero. So parallel force gives us no moment. The perpendicular force, that gives us our moment. And the amount of moment is the arm times how much force is perpendicular. So if we know this distance from the pivot point to the point of application, and we know how much of our force is perpendicular, we just have to multiply those two. If we know this angle, we can use some trig to figure that out. Our perpendicular piece is over here. That's our opposite side. The trig function that goes with opposite is sine. So typically with the angle defined this way, the perpendicular component involves the sine of the angle. That's why when the angle's small or zero, we get very little moment because the sine of zero is zero. When the angle is perpendicular, we're at 90 degrees, the sine of 90 degrees is 1. So the angle here controls how much of the force actually creates moment. All we have to do when we want to find the moment is we've got to find the perpendicular force. If we know how much force is perpendicular to the arm, then we just find that amount of force, multiply by the arm, and we've got our moment. So let's try that out here. So we do have to have a pivot point specified. You cannot just say you've got a moment of 32 foot-pounds without specifying what point that's about. 32 foot-pounds about the datum, 32 foot-pounds about the nose wheel. There has to be a reference point. It's just like measuring an angle. You can't just say 30 degrees. It has to be 30 degrees from horizontal, 30 degrees from vertical, clockwise, counterclockwise, all of that. One of the things we're going to be doing is combining moments. We'll be adding moments together. We're going to find here that when we have multiple forces, we have multiple moments. As long as all the moments are taken about the same point. So once we pick that pivot point, we only use that pivot point to find our moments. We can add or subtract those. If we have two different moments around two different points, we can't combine those together. They have to be about the same point. So let's try an example here. Here we've got a bar, and let's make that bar, let's see here. We'll see if I can, whoops, wow, my drawing skills are a little rough here. Let's try that again. Let's make this bar 10 feet long. There we go. So that's 10 feet long. And we're going to put a force on it. So let's say that's our force. We'll make that force, let's say 60 pounds. There we go. So we've got 10 feet and 60 pounds. If we pick our pivot point to be this end of the beam, now we can figure out our moment. Moment is force times distance. Force applied times distance away from the pivot point. The perpendicular force times that distance. Well, this force is all perpendicular to the distance. If we draw a line between the pivot point and the point of application, it would be right along the beam. So it would be a 10-foot long line times 60 pounds of force. Moment is force times distance. So we could write that down here. The equation essentially for moment is going to be moment is the perpendicular force times the distance from the pivot point. Well, we have a perpendicular force of 60 pounds times the distance of 10 feet. That'll give us 600 foot-pounds. Now we have one more thing we have to add to this here, and that is the direction. Moments have direction to them. There are only two possible directions, clockwise and counterclockwise. And you may remember from weight and balance, we made a choice about what moments to call to assign positive and what moments to assign negative. Since we only have two options, it makes sense to label one option positive and the other option negative. In the A&P program, and generally in weight and balance, we normally draw the airplane with the nose to the left. So clockwise moments tend to be those that take the nose up or the tail down. Those are considered to be positive, while counterclockwise moments are considered to be negative. Well, in the end, that's arbitrary. In the end, that there was no other choice involved there other than just someone deciding, well, this is what we want to do. The reason they picked it that way is to minimize the number of negative signs they would get when doing weight and balance problems. We have other restrictions in dealing with more complex systems. So we make a different choice in engineering. And this is typical in pretty much every other application other than weight and balance in aircraft. Counterclockwise moments are positive, clockwise moments are negative. Now, again, it's arbitrary, and you'll get the right answer as long as you're consistent. But the general default assumption is that counterclockwise moments are positive and clockwise moments are negative. So if we go back to our picture, we have to decide, is this going to be a clockwise or a counterclockwise moment? Or specifically, is this going to be a positive or a negative moment? Well, if this force pulls up 10 feet away from the pivot point, everything's going to rotate counterclockwise. And counterclockwise moments are positive. So counterclockwise moments are positive. So we could label this as a positive 600 foot-pounds. If we were taking a sum of moments, it would go into the sum as positive. Let's try another example here. Let's get rid of that 60-pound force, and we'll flip it around. Well, if we keep that same 60-pound force, we're going to have the same amount of moment. 60 pounds, 10 feet away, that's 600 foot-pounds. But now it's going to be a clockwise moment. And clockwise moments are negative by default. So we'd have to label that as negative 600 foot-pounds, or put in a sum as negative 600 foot-pounds. We got to take into account direction by watching that, by watching our signs. Well, what if we do something like that? If we have 60 pounds of force pulling on the end of this beam as illustrated, is this thing going to tend to rotate at all? Anyone there? Gonna see any rotation? No. Nope, no rotation. This is kind of like trying to open a door by pulling on the hinges or by pulling on the handle kind of along the length of the door. It's not going to get you any rotation. Might pull the door off the hinges eventually, but it's not going to swing the door open or closed. The line of action of our force goes right through the pivot point. So whenever the line of action goes through the pivot point, we have no moment. We still have a force here, and that's still going to be important for equilibrium. There is a force pulling this thing to the right with 60 pounds of force, but it's not causing a moment. It's not causing rotation. Now, let's say we have something like that. We've got this force at an angle, and let's make that angle, let's say we'll do 30 degrees. So if we have a 30-degree angle there, we're going to have to break this force up into components. So let's draw it out here on the board. We've got this 10-foot beam, and applied right at the end, we've got 60 pounds of force at an angle of 30 degrees. To figure out how much moment we've got about that pivot point, we've got to figure out the perpendicular component of the force. For figuring out the moments, we don't care about what the parallel component is. So we don't need to know the adjacent side here. What we really need to know is the opposite side. Because if we break this up into the opposite side and the adjacent side, it looks sort of like that. That'd be our adjacent. That would be our opposite. Pick that up and move it over there. Well, take a second here and figure out what's going to be the perpendicular component here. How much force are we going to have for the opposite side, or the y component, if we use our regular coordinate system here, x and y, what is our y component going to be for this 60-pound force? So it's the opposite side. We're going to take it off to the side, kind of do, we've got 60 pounds, we've got the adjacent side, we've got our opposite side.
30 pounds.
It's going to be 30 pounds. The opposite side goes with sine. So the opposite side is 60 pounds times the sine of 30 degrees. Sine of 30 degrees is 0.5, according to our calculator, and 0.5 times 60 is 30 pounds. So there's 30 pounds of force here perpendicular to the pivot point, or perpendicular to the line between the pivot point and the point of application. That's the only force that's creating a moment. Now, I think everyone would agree, if you think about your feeling or your intuition on this, if that 60-pound force is pulling up and to the right, there's definitely going to be rotation here. There's going to be a moment here, but there's not going to be as much as if 60 pounds was perpendicular. It's like trying to open up a door by pushing on an angle rather than pushing perpendicular to the door itself. So we're only catching a piece of it. We're catching half of it, but that adjacent side has much more. That's, you could figure it out, but we don't really need to here. We only need that perpendicular component, and that perpendicular component goes with the opposite side. Opposite side goes with sine. So we've got 30 pounds 10 feet away. The moment is the perpendicular force times the arm. So we've got 30 pounds of force times 10 feet of arm. That's 300 foot-pounds. So we've got 300 foot-pounds of moment. It's counterclockwise. So it'd be positive 300 foot-pounds. So those are some of the issues that we have to deal with respect to moment. When we have a moment involved, or we've got to find a moment, you've got to be focusing on that perpendicular component of the force. The parallel component does not contribute to the moment. Only the perpendicular component does. So effectively right here is taking that sine is the same thing we do when we're leveling an aircraft. We're making it so that the forces and the arms are perpendicular. So all we have to do is just multiply the two together. The hard work in balancing an air and doing the weight and balance on an aircraft is leveling it. The hard work here is using sine to figure out that opposite component. So if we flip the direction around, sine would change to a negative moment. Now, how moments are drawn? Moments are technically vectors. And while they're vectors, they have some sort of directionality to them. Because we're stuck living in a flat plane, those two directions are just counterclockwise and clockwise. In 3 dimensions, a moment could be in any direction you want. And it's part of what makes working in 3 dimensions a lot harder than we're working in 2 dimensions. So usually moments are represented in 3 dimensions, but since we're dealing with 2-dimensional problems, we only have 2 options for our moment. Positive and negative will do the job to distinguish the two. We can use a sine. And typically the way it's usually referred to is by the handedness of the rotation. A right hand rotation is positive, while a left hand rotation is negative. So it's another example of the right hand bias, I suppose, in science, engineering, and technology. Right hand seems to be good, left hand seems to be bad. How a right hand rotation works. Let me see if I can show you this here on the page. So there's my hand. Right hand rotation, if you curl your fingers in the direction of rotation, then your thumb points out at you. A left hand rotation would be in this direction. If you used your right hand to do a left hand rotation, your thumb would point down. So left rotation versus right rotation. We usually use counterclockwise or clockwise. That works too. But the right hand rotation is something else you might see referred to out there. But right-handed rotation, right hand is counterclockwise. Left hand, either that way or that way, would be clockwise. So how does this help us with equilibrium? Well, if a system is in equilibrium, it can only be in equilibrium if there's no moment. If there's a net moment on the system, then we don't have balance. You might remember from weight and balance that one of the definitions of balance is when all of the nose down moments and nose up moments add up to zero. Well, that's just another way of saying clockwise and counterclockwise rotations add up to zero, no net moment. If there's no net moment, the sum of moments equals zero, then we have equilibrium. If the sum of moments aren't zero, then things would start rotating. We have torque, we have a net torque, and things are going to start rotating. So a system can only be in equilibrium if the sum of moments about a point equals zero. And this is a true statement. It's a mathematical theorem. It could be proven. We're not going to prove it, but it can be. It's a useful benefit to us, though. It says that if the sum of moments about 1 point equals zero, then it doesn't matter what point we pick, any point in the system. If we take all the moments about that, we use that as our pivot point. Essentially, an airplane's in balance no matter what the datum is. If the airplane's in balance about the datum, then it's also in balance about the spinner on the prop. It's also in balance about the pilot's seat. It's in balance about the tail post. So it's no matter where we pick our point to do our math around, if it shows that we have no moment, then we have no moment with regard to any point. So it doesn't matter if you and your neighbor pick different points to analyze in the problem, it's still going to work as long as we're in equilibrium. And every problem we do is in equilibrium. So we're free to choose the pivot point as we see fit. And I'll show you along the way as we work more with moment in the coming weeks, how to be careful and pick a pivot point that will help minimize the amount of work you have to do. Picking the right pivot point can make the difference between a problem that takes some sophisticated math to do and a problem that just takes a little bit of algebra. It can make the difference between needing to use simultaneous equations and just solving algebraically without having to combine equations together. So if you pick your pivot point carefully, you can really simplify the problem. So in general, equilibrium of a system depends on two factors. We have to have the sum of forces and the sum of moments both equal zero. So the sum of forces in the x direction has to equal zero. The sum of forces in the y direction must equal zero. And the sum of moments about a point must equal zero. So those are our conditions for equilibrium. So for equilibrium, in order to have equilibrium, we need to have our sum of forces equal to zero, our sum of forces in the y direction equal to zero. So this is the sum of forces equal to zero. Our forces all have two components. So our x components have to add up to zero. Our y components have to add up to zero. And our sum of moments about some point, and I'm just going to label that P for some point, that must equal zero as well. So we have three equations. In a non-concurrent force system where moments are a thing, we end up with three equations. Now that seems more complex, and it is. We have three equations, but it's also more powerful because with three equations, we can handle three unknowns. In two equations, we could only handle two unknowns, two missing pieces. But now with a third equation, we can handle three unknowns. And although it seems at the face of it that that would be more complex, in practical problems, that tends to simplify things because usually tied up in our moment equation is something we're going to need for one of these two equations that we would otherwise need to do simultaneous variables or something like that to get. So the moment equation, although it's extra, it's on top of what we've already dealt with for concurrent problems. It does add a lot of useful information, and it makes it so that we can solve more powerful problems or more practical problems. So in general, we need all three of those to be true. It's a necessary condition. If we're in equilibrium, the sum of forces and the sum of moments will be zero, and vice versa. If the sum of forces and the sum of moments are zero, we're guaranteed to have equilibrium. So that gives us our equations of equilibrium, that the sum of forces and the sum of moments equals zero. So let's see how this works. We have just about enough time for an example problem before I give you some to work on your own in the practicum session. So let's see how this can work. So here is a non-concurrent force problem. We have this beam that has 100-pound weight sitting on it. Maybe this beam is an I-beam, or maybe it's a 2x4 or 2x6 sitting on its side, and we've loaded it up with 100 pounds. Well, let's draw that out, and we'll analyze it and figure out what the forces are that are unknown in the problem. So here we've got this beam, and these beams, although we might draw them with some thickness to them, that thickness is usually considered to be very small. So don't worry about how thick the beam is or anything like that. In fact, most of these beams, unless it's otherwise specified, these beams are considered to be weightless. In reality, they definitely have some weight, and we'd have to take that into account. But in structures, the weight of the beam is usually very small compared to the loads that are placed on that beam. So it's a reasonable assumption to eliminate it. So here we've got this 100-pound box sitting there. And let's make this thing, let's see, we've got a little roller right here. We got a couple of rolling pins or something like that this is sitting on, a couple of wheels that it's sitting on. Now, as long as there are no forces to the side, this is fine. It's not going to roll away on us. Let's put some geometry on the problem here. We'll put some distances in. Let's say we've got 4 feet there and 6 feet there. So with what's drawn on the page, we can figure out some things. What we're typically trying to figure out in these types of problems, and these are the types of problems we'll be mostly working on this week and a little bit into next week also. We are looking at trying to figure out what the supporting forces are. We've got this load placed on this beam. We want to know, how is that load distributed to the supports? If you think about this like a bridge going over a river or something like that, when things go across the bridge, they're pushing down on that bridge. That weight has to be distributed to the supports, to the abutments that support the bridge across its span. Well, that's usually what we're trying to find. We're trying to find the support forces. Now, those support forces only exert a force on the beam when we put a load on it. So if there's no 100-pound load, there is no support force. The beam doesn't weigh enough to really load up those supports. This is similar to something we looked at briefly a little while ago. When you set something down on, say, a table or something like that, that table has to generate a force to oppose the weight of whatever you set down. It has to generate a supporting force. In a sense, you can think of the structure as reacting to the load you've put on it. There is action and reaction. The action of setting the load down on the table, the reaction of the load of the table generating a force to hold that weight up. The support forces here are doing the same thing. When we set this load down, these supports are going to react, and they're going to react with just the right amount of force at those ends of the beam to keep this thing in equilibrium. So the body that is of interest here is the beam itself. The beam is our body. So if we draw our system boundary around the beam, then we can draw the free body diagram of that beam. So remember what the free body diagram shows. It shows the body without the imposed forces, the applied forces, and without the support forces. And remember that when you've got that system boundary, anything that crosses it or touches it has to be represented. So right here, we've got a 100-pound force pushing down. It's helpful in these types of problems to label the support points. And those are usually at the ends. They don't have to be, but they're usually at the ends of the beam. I'm going to call this one A and that one B. Now these two rollers, they're going to have to push up on the beam. Otherwise, this thing can't be in equilibrium. If this thing's pushing down, there needs to be something to push up on it to counteract it, to be in equilibrium. But we don't know what those are going to be just yet. So we're going to have to call them by some symbols. Since these are reaction forces, it's traditional to label them with the letter R. And to distinguish what point they're at, we label them with the letter of the point that they represent. So this is at point A, and this is at point B. And then to help us out a little bit in the future, because this is a very, very simple problem, they get more complex as we gain some skill with them. We can label the component direction here. Both of these point in the Y direction. If we use our traditional coordinate system, X and Y, both of these are in the Y direction. And it's helpful and helps us to get our equations of equilibrium faster if we label these with the Y component. So we have two unknown forces here. We have RAY, the reaction at A in the Y direction, and RBY, the reaction at B in the Y direction. And I've drawn this specifically below where the dimensions are here, so I don't have to redraw those. So it's clear that 100 pounds is 4 feet away from A, 6 feet away from B. The whole beam is 10 feet long. So there's our free body diagram and our coordinate system. Is anything not making sense about how I got the free body diagram? All right, so let's build up our equations of equilibrium. The first two are going to be the ones we've been doing all along that we did last week. So ones you should be reasonably familiar with. Let's do our sum of forces in the X direction. Well, if we go through the forces in the problem, we could do the whole formal process that we've been doing in our previous problems, label these as 1, 2, and 3, break out the components and all of that. But since everything's basically in the y direction, we can just kind of go through each piece. And in fact, in practical problems, these forces are most often already broken up for us. They're already in x and y components. So it's a lot easier in these types of problems to just kind of read things off. And to make sure I don't miss anything, I always go left to right across the beam. I start at the left end and I go to the right end. Well, if we look at each of the three forces we've got here, well, RAY doesn't have an X component. 100 pounds doesn't have an X. RBY doesn't have an X component. So I've got a whole lot of nothing in my X direction. So my X direction sum just says nothing. If I take my sum of forces in the y direction, however, I see something a little bit different. In the y direction, I've got RAY, and that points up. So it goes into the sum positive. I've got 100 pounds, but that 100 pounds points down. So it's negative. So I have a negative 100 pounds. And then the only other force in the problem is RBY, and RBY is in the positive direction. So that's our sum of forces in the y direction. We have 2 up and 1 down. Now's where we get to the part about moment. We've got to use our third equation because we can't solve this. If we set these equal to 0 now, we've got too many unknowns in one equation. We don't know what RAY is. We don't know what RBY is. So we can't solve for the other one. We need that moment equation to untangle the mess. So we need moments. To find the moments, we need a pivot point. So I'm going to pick a pivot point arbitrarily here. I'm going to pick point A as my pivot point. Now, it's arbitrary, but generally, you will simplify a problem if you pick one of your support points as your pivot point. And as we work more of these problems, you'll get to the point where you can just kind of read off the moments as you go along. But here, let's do this a little bit more formally. Let's look at our three forces. We've got RAY, we've got the 100 pounds, and we've got RBY. So let's try and figure out what the arms are relative to our pivot point, which is point A, for each force. Well, how far away from the pivot point is RAY? Well, hopefully I hear 0 there. It's pushing on the pivot point. So the arm is 0. Now, how about this 100-pound force? What's the arm for the 100-pound force? How far away from the pivot point is the 100 pounds?
4 feet.
It's 4 feet. So we got 4 feet there. How about RBY? Remember that once we pick our pivot point, we've got to measure to all the positions from that pivot point. I like to, when I teach weight and balance, I like to say, imagine the end of your tape measure is welded to your datum. So everything has to be measured from that point. So how far away is RBY from the pivot point? What's our arm there?
10 feet.
10 feet. By far, the most common error I see people make in working these problems is forgetting about the arm for this far point force, for the one that's farthest away. If you get kind of ridiculously high answers for your forces, like you're supporting 100 pounds, but you get something like 1,000 as your support force, chances are you've forgotten the arm somewhere. So you got to be careful. Well, let's figure out our moments here. Well, RAY we don't know, but its arm is 0, so we know its moment. Arm times force is moment, and all of these are perpendicular. So these are our perpendicular forces, no sines or cosines needed. The moment is 0. We have our 100-pound force 4 feet away. We can multiply those and we get 400 foot-pounds. Now RBY is 10 feet away. So if we're pivoting at A and we push up with some amount of force here, we would certainly expect this thing to rotate. So RBY definitely has a moment associated with it. We just can't write down anything but an expression for it. The best we can really do is say it's going to be 10 times whatever RBY is. If RBY is 3 pounds, then it's going to be 30 foot-pounds. So those are our moments. Now, I haven't taken into account direction yet. I haven't set the signs on these yet, just like when we did with our sum of forces. We'll do that in the sum. So let's do our sum of moments about point A. Well, RAY pushes right on the pivot point. So it's got 0 moment, so we don't even need to consider it. We've got our 100-pound force 4 feet away, so that's 400 foot-pounds. We don't really need to include the foot-pounds in there, but 400 foot-pounds. But then we have to figure out direction. If we're pinned at A and we push down, this thing's going to rotate clockwise. And clockwise moments are negative. And to help us remember that clockwise moments are negative and counterclockwise moments are negative, we make a little bit of an addition to our symbol for the coordinate system. We add in the direction of positive moment. Remember what these arrows are telling us. Direction of positive X, direction of positive Y. Remember, right-hand rotations are positive. So we'll often write that. That little curly arrow labeled M is reminding us that counterclockwise moments or right-hand moments are positive. So we have 400 foot-pounds counterclockwise. So that goes into the sum negative. Then we've got RBY. RBY is pushing up. So that's going to create a counterclockwise moment. Counterclockwise moments are positive. So we'd have plus 10 RBY. So there we have our 3 sums. The sum of forces in the X direction, the sum of forces in the Y direction, and the sum of moments about a point. To make these a set of equations, we have to use the fact that we are in equilibrium. And in equilibrium, each of these sums must be equal to 0. So just like in our concurrent problems, we go through and set the sums equal to 0. Well, that first sum tells us a whole lot of nothing. 0 equals 0. Yeah, true, but it doesn't buy us a whole lot. The other 2 equations are a little more useful. We've got RAY minus 100 plus RBY equals 0. And we've got minus 400 plus 10 RBY equals 0. Well, we can't solve this one just yet, but we can solve this one. If we add 400 to both sides, we'll get 10 RBY equals a positive 400. Divide both sides by 10, and RBY equals 40. Don't forget the units, that's 40 pounds. So that's telling us that RBY is 40 pounds. Now that we know that, we can go into our X direction, our Y direction equation and replace RBY with 40 pounds and solve for RAY. Negative 100 plus 40 is negative 60. RAY minus 60 equals 0. So RAY is 60 pounds. So we found our missing pieces. We found our two support forces. We have 60 pounds of force pushing up at A, and we have 40 pounds of force pushing up at B. Now, whenever you're working any of these problems, once you get to this point and you have solved for your unknowns, you should take a little step back and think whether or not it makes sense. Does it make physical sense the way this is set up? Does it make sense that A, the support at A, would be bearing more load than the support at B? And sometimes just in your head, it's a benefit to kind of move the force around a little bit. All of this is happening because that 100-pound force is sitting on that beam. If you move that 100-pound force, how would you expect things to move, or to how would you expect the load to change? Well, if that 100 pounds was sitting much, much closer to A would be supporting most of that 100 pounds. If it's far away from B isn't going to be supporting very much of it. It might support a little, but not much. The load is closer to A than it is to B. So we expect A to handle more force than B does. So this makes sense. So it at least looks like a reasonable way to load the beam. So let's step back here and see and review what we've done. So we had this problem. We had a 100-pound box sitting on a beam, and we wanted to find the reactions at the supports. We wanted to find out how hard those supports had to push up to keep this thing from moving. We drew our free body diagram where we found our support forces, RAY and RBY. We took our sum of forces in the X direction and found nothing. We took our sum of forces in the Y direction, which basically said the forces pushing up have to be counteracted by the forces pushing down, RAY minus 100 plus RBY. And then we found our moments. We recognize that this is a non-concurrent force problem because the lines of action of our forces do not intersect. So we needed moments. We picked a pivot point at A, and then we found the moment of each of our forces relative to that pivot point. We made a little table here, and if that table helps you, go ahead and use it. In future problems, we'll just kind of build the equations directly. We've got no moment here. We've got 100 pounds 4 feet away, so that's 400 clockwise, negative, and so on. So we'll go a little bit more quickly on it on future problems. But if that table helps you, definitely make it until it makes sense to you. We found our sum of moments had to be 0. We could solve that equation, and that gave us our support at B. And then knowing the support at B, we could back solve into the Y direction equation and find the support force at A. That is, in essence, the basic non-concurrent equilibrium problem. Now, there's a lot more to know about these supports and the different kinds of supports that we can have, and those factor into a lot of the things we'll be doing in Wednesday's class, and a little bit in Monday's class as well. We'll look at supports and how the different supports are represented in the free body diagram. But I'll do another example in the practicum session, and then I'll give one for you to do to practice on your own. So let's finish up the formal notes here, and then we'll take a break. So next time we'll be getting into our support mechanisms. We'll look at things a little more sophisticated than rollers, and we'll look at how these reaction forces are represented in free body diagrams. We'll spend most of our time on Wednesday night practicing on non-concurrent force problems. All right, so we are going to, we'll take about a 10-minute break or so. And when we come back, I'll do another example of a non-concurrent force system, another beam kind of problem, just set up a little bit differently. And then I'll provide one for you to practice on and debug your skills a little bit. So we'll take a break, back in about 10 minutes. All right, to start off our practicum session tonight, we'll look at another non-concurrent force problem. We'll do another beam problem, but this time instead of having the beam supported by a by supports on the ground, we'll have the beam hung up by a couple ropes. So we'll have one rope there, and let's see, we'll have another rope over here, making a 60-degree angle to horizontal. And then we will, so these will be attached to the ceiling. And let's load up this beam with a little bit larger forces than what we've been using here. We'll switch our units a little bit into kips. Kips is something we talked about briefly at the beginning of the class a few weeks ago. Kips is shorthand for 1,000 pounds. So we'll put, instead of putting a 1,000-pound box on this, we can put a 1 kip box on it. The important thing to keep in mind is to make sure we stay consistent with the units. So if our forces applied in the system are all in kips, our answers are all going to be in kips too. We're not going to mix. I don't think I have any problems where we mix kips and pounds and play unit games and such like that. It's just trying to make sure that we get the right amount of the right units, the right answers, and the right procedure. So let's see here. We'll apply let's put a couple of loads on this one. And let's see. I think we'll have a 2 kip load there. So 2 kips there. And then I am actually going to have a force at an angle here. So this will have a couple of different factors involved. Let's push this one down at an angle of 45 degrees. So you've got something that's coming in on an angle, and we'll make that 3 kips. And we'll put some geometry on this. We'll make everything measured out like that. Make this 3 feet. We'll make this 4 feet. We'll make that 1 foot. Now our goal in this problem is to find the tension in the wires. So we want to find our tension. And let's see, this is always the problem with designing a problem on the fly. You have to try to work out the solution ahead of time, and sometimes you back yourself into a corner. So I'm going to change one thing in the problem here to make it a little bit more realistic, and I'm going to eliminate this angle right here. So no angle right there. We're going to try and find that angle. So we're going to need a value there. I don't know exactly what that angle is going to be, so we'll call it theta. So we don't know what that's going to be just yet. So there's our setup. And what we want to find is the tension in the ropes and that unknown angle. So this is going to bring in a fair bit of what we've worked with before as an example. The one I'll have you work out on your own will be a little bit simpler. But this is a good overall practice of a number of skills that we've worked with so far. So I'm going to call this one, let's call that T1, and we'll call this guy T2. So we've got two ropes, and we want to find the tension in each of those ropes and the angle T2 makes to horizontal. So let's start by figuring out first our free body diagram. So the free body diagram, the beam is going to be our body. So that we'll keep that. But everything that touches it, we're going to have to represent in our free body diagram. So if we have this system boundary wrapped around here, everything that touches or cuts through or pierces that boundary needs to be represented by a force. Now, since ropes can only be in tension, they must be pulling up here. Couldn't be in equilibrium if these weren't pulling up. So we have T1 pulling up there. We have our two kips pushing down there. We have our three kips at 45 degrees pushing down there. And then we have this unknown T2 at our unknown angle. We can also define our coordinate system. To the right is positive x, up is positive y, and counterclockwise moments will be positive. Anything not quite making sense on the free body diagram? All right, so we've got our free body diagram. We have to proceed a little more carefully in this problem because it's a little more complex than the last problem that we looked at. We've got a couple of forces at angles here. So we're going to have to deal with the angles, just like we did in the problems last week. When we have vectors at angles, we have to find the components of those vectors. Now, we met this situation a couple times last week where we knew nothing about the vector. And when you know nothing about the vector, it's safest to just label its components as x and y rather than trying to do sine and cosine of the angle and T1 or T2. So I'm going to draw in red my components here so that they'll stand out a little bit. This one right here, that would be T2 in the x direction, or T2x. Get the focus a little better there. And the vertical component would be T2y. So that's T2 broken up into components, T2x and T2y. Those are going to be easier to work with and solve for than dealing with T2 cosine theta or T2 sine theta. That gives us ugly equations that'll be a mess to deal with. Once we have numbers for T2x and T2y, we can use the Pythagorean theorem and inverse tangent to figure out our angle. We've also got this 3 kip force, and now we've got to be careful. Notice how I drew the components on this one. I started out at the tail, and I drew outward because that's what the vector does. It starts at the tail and goes outward. This one is applied as a pushing force. So to draw my components, I'm actually going to draw them both as kind of pushing forces. I'm going to draw my X component like that and my Y component like that. And I'm doing that because I want to be clear that that force is applied at this point. If you start drawing over here, you can sort of get yourself into some trouble starting to think about, well, where is that point? How far away is it? All of that. And you go down all sorts of bad paths. The force is applied right there. So that's where I'm going to make the components apply, just like I did over here. The force is applied here, so the components are applied there too. If you keep those clear, then you'll have an easier time coming up with your equations. Now the angle here was 45 degrees. So to figure out our components, we'd need sine and cosine of 45 degrees. Fortunately, 45 degrees, sine and cosine are the same. So to figure out our components here, which I can label here, hopefully you're getting familiar enough with this now that you can just kind of go to your calculator and do 3 cosine and 3 sine and figure out which one they go to. But if we go to the adjacent piece, that would go with cosine. So 3 cosine of 45, we get 2.1213. Kips pushing to the right. And we have, for the vertical component, 3 kips, 3 kips and sine of, because that would be the opposite side, sine of 45. So that should give us the same thing, 2.1213 kips. And I am keeping 5 sig figs, so I'll round my final answer to 3. So now we've got all our forces broken up into X and Y components. That'll help us out. Any questions on breaking these forces up? All right, so let's go ahead and do our sums. So just like a problem we did last week, we do our sums of forces. Sum of forces in the X direction and sum of forces in the Y direction. But rather than labeling each of them out and doing the X and Y components, we'll just jump right to it. Going left to right, I've got T1, that's all Y, so no X. I've got 2 kips, that's all Y, no X. Over here, I've broken up my 3 kips into a horizontal and a vertical. There I do have something to the right. That is 2.1213 kips. We don't really need to label that. It's to the right, so it's positive. The only other X component I've got is this T2X. And I've kind of made an assumption here by the way this is drawn. You could think of this as being something somebody sketched up. They didn't actually go out and build it. They sketched it up to see if it would work, to do this kind of analysis. And maybe they weren't sure whether this rope had to angle to the right or to the left. So they took a guess and they made it angle to the right. So we have to go with that assumption. T2X points to the right, so it goes into the sum positive. We'll get a check on that assumption when we do the math. If the answer comes out positive, the assumption was good. If the answer comes out negative, then the assumption was bad, and we'd have to go back and redraw things at the end of the problem to get a better picture of how things look. So that's an important idea that's going to come back several times. So I want to make sure we cover that here. So there's our sum of forces in the X direction. Nothing else in there in the X direction. So let's go to our Y direction. Sum of forces in the Y direction. We've got T1 up, so that's positive T1. We've got 2 kips down, so that'll be negative 2. We've got 2.1213 down. So that goes in negative. And then we've got T2Y. So that's our sum of forces in the y direction. Basically what we would have done in problems we worked on last week. Any questions on the x or y direction equations? So now we come to the new part. We've got to do our sum of moments about a point. And like I said a little earlier this evening, it's always going to be an advantage to pick your pivot point to correspond to one of your support points. That usually makes things easier because it eliminates an unknown. When you put your pivot point at the point of application of some unknown force, you don't have that unknown force show up in your moment since it has no arm. Now, generally, if you know nothing about your supports, any support point will do. We could pick the attachment point for T1. We could pick the attachment point for T2. And since I did the attachment point for the left side in the first example, I'm going to do the right side in this one. So I'm going to pick this point here, which I'm just going to label B as my pivot point. So I'm going to want the sum of moments about point B. So point B is my datum. Point B is my reference point. And all the moments are going to be, all the arms are going to be measured from B, and all the directions of rotation are going to be considered as if B was nailed to the wall. We've got a pivot point running through that, and everything else is causing rotations about that pivot point. So B is going to be my pivot point here. So now we can go through and figure out the arms for each of the forces and the amount of moment for each. Now, we've really got 1, 2, 3, 4, 5, 6 forces to consider. The 4 components in red, which were split up from our 3 kips and our T2 force, and then these other 2 that were already lined up perpendicular. So let's kind of go through each one by one and figure out the arm and the moment. So for T1 is looks like 8 feet away from our pivot point. Got 1 foot plus 4 is 5 plus another 3 is 8. So we've got an arm of 8 feet times a force of T1. What T1 is, not sure, but whatever it is, 8 times it will be the moment involved. Then we have to figure out, is that positive or negative? Well, if we pin at B and push up at T1, that'll cause a clockwise rotation. And according to our coordinate system, clockwise rotations are negative. So we'd have negative 8 T1 generated from the left-hand supporting rope. We go on to the 2 kip force. We have to figure out the arm for the 2 kip force. Well, the 2 kip force looks like it's 5 feet from the pivot point. It's 2 kips perpendicular. So it's all those 2 kips times 5 feet. That gives me 10. The units would be kip feet or foot kips, which sounds a little weird, but just means thousands of foot pounds or thousands of pound feet. If we're pushing down here and pivoting at B, if I push down here, that'll cause a counterclockwise rotation. And counterclockwise rotations are positive. So I get a positive 10 kip feet there. Then we've got our 2.1213 kip forces. Now this beam is pretty thin. So the line of action of this horizontal piece goes right through B. So that means it has no arm. So the horizontal 2.1213 kip force doesn't generate a moment because it's pushing along the hinge line. It's pushing right at the hinges. So it's not going to cause rotation. Only the perpendicular components cause rotation. So this 2.1213 kip force does create a moment. It's 1 foot away. So it's 2.1213 times 1, or just 2.1213. Pinned at B, pushing down counterclockwise. So it's positive. And then we get to point B and T2X and T2Y. Well, T2X is pulling on the pivot point. T2Y is pulling on the pivot point. So no reaction or no moment there at all from either of those two. The force T2 pulls on the pivot point, so it doesn't create a moment. So there's all we've got in our sum of moments. We've got -8 T1. We've got 2 kips 5 feet away, so 10, and 2.1213, the vertical part, 1 foot away. So that's our sum of moments. Now to make these into equations, we set them equal to 0. So unlike the previous problem, now we've got 3 sums of, or we've got 3 equations. Fortunately, 2 of them are pretty straightforward to solve. The first one only has 1 unknown in it, T2X. The last one only has 1 unknown in it, T1. So since our moment equations are new equation, let's go ahead and work with that one first. So first we can simplify it down just a little bit and say it's -8 T1, but then we can combine the numbers together. So the rest of this is algebra at this point. We've got 12.121. I'm rerounding that to 5 sig figs. That equals 0. I'm going to add 8T1 to both sides. So I have 12.121 equals 8T1. Divide both sides by 8. 12.121 divided by 8. We get T1 is 1.5152, or sorry, 1.5151. Let's try that again. 1.5151. And the units are kips. So we know what T1 is now. T1 we assumed was up, which only makes sense from the drawing. And we found a positive answer. That means our answer, our assumed direction was correct. T1 is 1.5151 kips. Now that's not the entire story, but it's 1 out of 3 of our variables. So we'll go ahead and write that down over here, 1.5151 kips. Now let's go to our x direction equation. The x direction equation is pretty easy to solve. All we have to do is subtract 2.1213 from both sides. And if we do that, T2x comes out to be negative 2.1213 kips. So we've got an answer that's negative. Negative answers mean we assumed the wrong direction. So negative answers mean we assumed the wrong direction. We assumed that T2 pulled to the right. But we find out here in this situation, T2's actually got to pull to the left. It wouldn't be physical for it to pull to the right. That's why we get a negative. We've got to stick with that negative for now, but we'll fix it when we draw a summary at the end of the problem. But for now, we've got our value, at least in magnitude. The x component of T2 is 2.1213. It just happens to be in the other direction. And then finally, we've got our y direction equation here. I'm trying to block off some of this here so we have some room. our y direction equation, we can simplify it a little bit here. This would be T1, we already know, is 1.5151 kips. If we combine the numbers together, we have 1.5151 minus 2 minus 2.1213. So that gives us minus 2.6062 plus T2y equals 0. If we add that 2.6062 to both sides, we get T2y is a positive 2.6062 kips. So that came out positive. Positive answers mean our assumed direction is good. So we assumed up, it is up. So the signs of our answers verify or contradict our assumptions about direction. So when we have to guess, or a guess is made for us, sometimes these problems are set up like this and you have to figure out the drawing's wrong. So if you get an answer that's negative, that just means that should be in the other direction. So there we've got our unknowns. So let's fix up the drawing a little bit, and then we'll we'll give our final answers. So if we redraw things a little, let's go back to our free body diagram. If you redraw things, you should always wait until after you've got all the values. Once you have all the values, then you can draw things in the right directions with the right numbers. So, and then you can finish up the problem. So here we've got T1, which we figured out was 1.5151 kips. That was our value for T1. We had 2 kips there. We had our 3 kip force here. And then we had T2x and T2y. But what we find is that T2y is up, and we found that was 2.6062 kips. But T2x has to be to the left. T2x was to the left, and the value there was 2.1213. That means the supporting rope is up and to the left, which kind of makes sense if you think about it physically. If you are pushing to the right, or something is pushing to the right, there has to be something else pulling to the left to cancel that out. This support isn't doing it because it's just vertical. So it's got to be this support. It's got to be pulling to the left. To answer the problem, we need this angle and that magnitude. So let's go off to the side here and redraw that in X and Y components. I'm going to draw X first, then Y, so that I can get my hypotenuse in the right place and the angle in the right place. Remember, when you're trying to find your magnitude and direction, you want your triangle to include the angle that you're looking for. So since I'm looking for the angle to horizontal, I'm going to do X first, then Y. So X first, I've got 2.1213 kips. Then I've got Y, 2.6062 kips. My magnitude is there, that's T2. And there's the angle I'm looking for. So we've got 2.60626. Oops, I transposed some digits there. 62. Let's rewrite that down here. 2.6062 kips. So we've got our X and our Y components. You can use the Pythagorean theorem and inverse tangent from here. So this is just like what we've done in the past. 2.6062 squared and 2.1213 squared. Add them together, take the square root. looks like our magnitude T2 is 3.3604 kips. And our angle is going to be the inverse tangent of 2.6062 over 2.1213. Inverse tangent of opposite over adjacent. So we take our inverse tangent and we get our angle is 50.856 degrees. So now that we've got our answers, we don't have any other calculations to do. We can round things to our final number of sig figs, which was 3 in this problem. So we'd round T1 to 1.52 kips. We'd round T2 to 3.36 kips. And we'd round the angle to 50.9 degrees. So that's what we'd have for our answer. So reviewing what we did in this problem, we had a drawing provided for us, which may have errors in it, might not be drawn the way it physically needs to be. Bear that in mind. It happens all the time. Not just in problems I make up for you, but problems out there in reality. Somebody hands you a sketch and says, hey, build this or analyze this, and it can't be the way they drew it. And you sometimes have to figure it. Sometimes you can see it immediately. Sometimes you have to figure it out by looking at the drawing or by doing the analysis and having things not work. So we had this drawing. We drew our free body diagram. We broke up all our forces that needed to be broken up into components. We took our sum of forces in the x direction, set it equal to 0. We took our sum of forces in the y direction, set it equal to 0. The new thing, we took our sum of moments about a point. I arbitrarily picked point B. You could go back and pick point A and rework the problem and see that you get the same answers. Pick the other end of the beam and try that out. We figured out the moment from each force, sign being set by clockwise versus counterclockwise, arm times force. Don't lose those arms, you'll get weird answers. In fact, you would have predicted here that T1 was like 12 kips if you forgot that arm. And then you get really strange answers from there. Like the fact that this rope would have to be pushing, things like that. It gets very strange. So if weird answers start coming up, go back to your moment equation, make sure you had an arm in there. It happens very, very frequently. We were able to solve the moment equation for our force at the other end. That's usually how it works out. We pick a pivot point at one end, it'll give us the force at the other end. Then we were able to solve our x and y directions. Then the rest was just cleaning up and getting the answer into the final form that they wanted, the magnitude and direction of the unknown forces. All right, so there's a lot to decompress there. So I would encourage you to kind of step through that one and maybe go back and watch the video again and see how that one worked out. A lot of different concepts coming into play there, especially the assumed directions, the signs, and all of that. Very important stuff, but good to get in early. So we've got a few minutes left here. So before we go to the next setup, any questions on this one? Any place where you had an issue or something else you wanted to look at on it? All right. So let's try a slightly simpler problem for you to kind of set up, and I'll give you a few minutes to set it up, and then we'll kind of work through the solution just to fit within the time before class is finished. So we'll do a similar kind of rope problem here, but this time everything's going to be vertical. We've got T1 and T2. We'll put a 5 kip force there. We'll put an 8 kip force here. And let's see, those are strapped to the ceiling. And then we'll make some geometry here. We'll say the distances. We'll go with 2 feet, 8 feet, and 3 feet. All right, so the goal is to find T1 and T2. So take a few minutes, write up a free body diagram, and start doing your sums of forces and moments. And in about 4 or 5 minutes or so, I'll get things set up and we'll do our solution. So I'm going to pause here. So if you have any questions, you can ask off the recording as we're setting things up. All right, so the first step is to draw the free body diagram. So to help us out, we can draw our system boundary. Anything that crosses, touches, or pierces that that system boundary must be represented. So we've got our beam. We've got T1, and since it's a rope, we're going to pull up. We got T1 there. We've got our 8 kip force down. We've got our 5 kip force down. And we've got our unknown force, T2. We can define our coordinate system. To the right is positive, up is positive, and counterclockwise moments are positive. So let's do our sum of forces. In the x direction, there's nothing in the x direction, so a whole lot of 0 for our x direction forces. Sum of forces in the y direction, left to right, we got T1 up, so positive T1. We've got 8 down, so -8. We've got 5 down, -5. And we've got T2 up, plus T2. Then we've got our moments. To find our moments, we need a pivot point. I'm going to pick the point right where T1 is attached. Doesn't have to be the exact end of the beam. It just has to be where that support is. So even if there are overhanging sections or anything like that, they're not going to matter. It's where that support is attached. So I'll call that point A. Now T1 won't have a moment about point A. It's pulling right on the pivot point. The 8 kip force, however, will have a moment. The 8 kip force is 3 feet away, so I have an arm of 3 feet. All 8 kips counts because it's perpendicular. So 8 times 3, I've got 24 kip feet. Clockwise, if we're pinned today and pushed down, we have a clockwise moment. Clockwise moments are negative. Then we've got our 5 kip force. The 5 kip force looks like 11 feet away. So we've got 55 kip feet, also clockwise, so negative. And then we've got T2. T2 will definitely have a moment, counterclockwise, so it'll be positive, but it is 13 feet away. So the best we can do on that one is say 13 T2. Don't forget that arm. Very common loss to a very common mistake to lose that. Since we're in equilibrium, all of these must equal 0. Well, 0 equals 0 doesn't buy us much. The second equation, we have too many unknowns to solve. We don't know T1 or T2. The third equation, however, we can solve. If we combine together the numbers here, we've got -24 minus 55. That gives us a -79. Adding 79 to both sides, we get 13T2 equals 79. Divide both sides by 13, and T2 equals 6.07692. And since I want 4 sig figs, I'm going to keep 2 more. I'm going to keep 6. So 6.07692 kips for T2. Now that I know T2, I can go and plug it in here to solve for T1. So I've got 6.07692. And that equation is pretty simple to solve. Just don't be so quick with your calculator that you lose the signs. If you combine it together, you're going to get a negative value here. Remember, you have to add that to the other side, so it'll be a positive. So if you're getting into the habit of jumping right to your calculator, just be careful with your signs. So that's 6.07692. So that'll give us T1 minus all these numbers together give us 6.92308 negative, which when we add that to both sides, that'll give us T1 is 6.92308 kips. So a little bit more load on T1 than on T2. And that kind of makes sense because although we've got 8 kips on one side, 5 kips on another, more of it's closer to T1. So there's a heavier load there. So to finish up, we would round our answers to our final number of sig figs. So T1 is 6.923. And T2, 6.077. Tips, not a bad idea to box your answer in. And there we go. Any questions there?
Nope.
All right. So that's it for tonight. Have a good remainder of the evening. Try not to get blown away. The gusts are up to about 50 miles an hour now. So stay safe, and I'll see you Wednesday night.